This is Britt Caswell with another example video. In today's video, I am going to be covering additional practice for graphing trig functions. So when we're graphing trig functions, the first thing that we want to do is we want to look for the transformations that happen within the trig function. Alright, so in this function, here at the top right, we are multiplying the function by 3. So you should know from previous experience with transformations that this is going to produce some kind of vertical stretch. What that means is that we're grabbing the top and the bottom of the graph and we're pulling those points away from the x-axis. So where a sine function normally goes from -1 to 1, now it's going to go up to 3 and down to -3. And so knowing those transformations, what I can now do is I can now label my x-axis in a way that I can really stretch this graph out on my paper. All right, graphing using small graphs is very difficult for many students. So make sure that when you are graphing trig functions that you take the time to make your graphs nice and big so that you could see where your anchor points are. Now, the values for our x-axis are coming from our unit circle. I could probably pull one of those up for you guys. So on the unit circle, remember it's talking about degree or radian measurements. All right, and so on our x-axis, what we're going to do is we're putting tick marks essentially for every 90 degrees. However, we often don't use degrees for these graphs. We talk about it in radians. So that's where I'm getting the 0, pi over 2, pi, and 3 pi over 2. And back to 2 pi, but so it's just every 90 degrees. Now, usually before I ever graph a trig function, I always do what we did to figure out what transformations are happening. That way you can adjust your graph easily, because there's a lot to move around if you run out of space. Now recall, with the unit circle, our sine function is all the y values here. So what I'm going to be doing is I'm going to be dragging these anchor points following that same pattern. So at 0, the sign is 0. At pi over 2, the sign is 1. Then 0. Then -1. And then 0. So you get this really nice curve. So this is the parent function, and then we're going to go ahead and do that vertical stretch to that parent function. All right, so what that means is that we look at the distance of each point to the x-axis, and we are tripling it. These 3 points that are on the x-axis, they don't change because their distance from the x-axis is 0, and 0 times 3 is 0. So those 3 stay. But this one that's up here at the top is going to go up to 3, and this one down below goes down to -3. And we can connect this with our curved line. Now remember, the sine and cosine functions are not zigzags. They are smooth curves. So it's important that you guys are trying to make them look like smooth curves. So what we have done is we have done one period of the sine wave. All right? Notice it takes from 0 to 2 pi on my x-axis, so that's what I'm going to write for my period. But what this does is this gives us kind of like a stamp, which we can repeat across other intervals on the x-axis. So for example, if I wanted to come here to the negative axis, I would just follow that same pattern. So I start at 0, I go to 3, I go to 0, I go to -3, and I go back to 0. And when I connect these, it looks like one solid curve, right? It meets back up with itself. That's pretty important. So now let's identify some of these key features. So my amplitude is this distance here. This is if I was measuring with a ruler, okay? And so you could see that's a distance of 3, and your amplitude will always be a positive number because it's measuring a distance. A phase shift is if we moved every single point to the left or every single point to the right. We did not do a phase shift on this, though future examples will have that. And a vertical shift is similar to a phase shift, except it's going up and down. Now, we did move some of them up and some of them down, but a vertical shift requires you to take all 5 points and move all 5 points together. So there is no vertical shift here. We have a minimum at -3, that's where the bottom of the graph is, and a maximum of 3. And then our midline is where this kind of Orion's belt kind of thing is at. I look at the vertical shift to determine my midline. So our midline here is at y = 0. And remember, you have to write that as an equation because lines are described with equations, not just numbers. Let's try another one. So on this one, we're going to be dealing with the cosine graph. It's being multiplied by -2. So there's actually 2 transformations that are happening here. We're dealing with the negative that's here in the front, and then we're dealing with the 2. So understand that there's 2 transformations here. So when we multiply a function by a negative value, you have a vertical reflection. And when you multiply it by 2, you're going to have a vertical stretch. So when we go to make this graph, instead of it going between 1 and -1, it'll go between 2 and -2. And on the x-axis, we're not stretching or compressing or sliding on the x-axis at all, so we can use our usual 4 points that we like to use. Alright, and I'm going to go in the backwards direction just to get some practice with copying it over an interval. Okay, so let's start with the cosine parent function. Remember, that comes from the unit circle looking at all the x values. And so it starts at 1, it goes to 0, down to -1, back to 0, and then up to 1 again. So when it's just points, it looks like a V shape. But remember, these are nice, beautiful curves. So when you draw that in, don't draw it in all pointy. It's not a zigzag. All right, so let's start with that reflection. All right, when I'm choosing my order of transformations, I always go from left to right. You need to deal with the multiplication before you deal with any addition or subtraction. Alrighty, so our first thing that we see is the vertical reflection. That means that we are taking this shape and moving it upside down. So if you have any positive y values, they are now negative y values, and the negative turn positive, leaving you with this upside down V shape. And then what that 2 is doing is that 2 is stretching us away from that x-axis. So we look at the distance from the x-axis to the point, and we double it. So instead of being at 1, this goes to 2, -1 to -2, and the same over here. And once we've completed all of those transformations, now we can draw in that nice curve. Now anyone that knows me knows I can't draw, so please don't judge me for that. Now I can copy this same curve over this interval, right? So I could start at -2, go to 0, go to +2, go back to 0, and then go to -2 again. And I can repeat that same curve that I just drew. I mean, I don't know how to draw very well, so it's kind of messy. But do you see how it meets right back up with itself and it's making that pattern go again? Alright, so now let's describe these things. Alright, some of them are pretty dang easy to do, right? Like your minimum's -2 and your maximum's +2. Most students get those right away. We did not shift the graph up or down at all, so our midline is at y = 0. And that vertical shift I just described is 0. We didn't move the graph to the left or to the right, so our phase shift is 0. The period and the amplitude are really the two that we tend to struggle with. Remember, your formula for the period, if you ever need it, is 2 pi over b is equal to the period. And your b is whatever number's in front of the x. So in this case, it's a 1. So our period is just 2 pi divided by 1, which is 2 pi. And then our amplitude is the distance from the middle of the graph to the top of the graph. So our amplitude in this case is 2. All right, here's another one. So this time what we're doing is we are subtracting pi over 2 inside the grouping symbol. So anytime you have something done in the grouping symbol, it's a horizontal change. This addition or subtraction that you see here is a horizontal slide. We call that a phase shift. All right, and remember, anything that's horizontal will always kind of feel backwards. So you see the negative pi over 2 and you feel like it should go towards the negative numbers, but it actually goes towards the positive numbers. So we are going to do a slide to the right by pi over 2. So what that means is when I go to draw in my usual lines, here's 2 pi, right? I need to leave enough space to go to the side by another set, right? Another tick mark, because from 0 to pi over 2 is 1 tick mark. Alright, so there I've set that up. I'm going to go ahead and set it up on the negative side. Now that being said, we did not talk about any vertical changes now, right? This one's just horizontal. So what that means is that my graph is going to bounce between 1 and -1, and I don't need to go hog wild on my vertical axis. Alright, so the cosine points, right? You should get your little U shape going. And so now that we have that U shape, now we're going to move each of these over to the right by pi over 2. And so remember, just look on your x-axis and see how many tick marks that is. So depending on whatever scale you're using down here, that might change. But in general, it's just that 1 tick mark. So I'm going to pick up every single point here and scoot it to the right by 1 tick mark. All right, now I can draw in my nice little curve. Now, if I wanted to copy this, remember I'm not just jumping straight over to the negative side. If I want to make another iteration of this curve, it has to touch. So here I'm starting at 1, going to 0, going to -1, back to 0, to negative pi over 3. And so here we are with a kind of okay curve. But see how it connects and it's still a smooth pattern. Alright, so looking at these periods, in this case, right, we didn't stretch the graph horizontally or compress it horizontally. So our period is 2 pi. In terms of amplitude, we did not stretch the graph vertically, so from the midline to the top is still 1. Our phase shift, we moved this to the right by pi over 2 units. But we did not have a vertical shift, right? We did not move it up or down. Our midline is still at y equals 0. And then our minimum is that -1, and our +1 is our maximum. A lot of examples, y'all. A lot of examples. Let's look at number 6. So now number 6 is still going to be a phase shift because you see that subtraction in here. But we have to remember the general form of these trig functions. They usually look like this. Alright, so when we have this general form of the trig function, do you see how we have like a double set of parentheses here? We don't like to have a number directly touching the x. We like it to kind of be, in this quarantine, socially distanced here. So when we don't have our expression written in this form, we can't accurately define what our phase shift is otherwise. So what I'm going to do on our equation is I'm going to factor that 2 out of this expression. So 2x divided by 2 is x, and pi divided by 2 is pi over 2. And so now you can see that phase shift a little better. So our two expressions that we're identifying transformations are the 2 and the -pi over 2. That's just like our last one, right? The -pi over 2. That's going to move us to the right in a phase shift by pi over 2. Heck, if I wanted to, I could write that right down here, right? Now this 2 you guys might not be used to seeing so much. We tend to avoid talking about horizontal shifts before we get to trig. Most teachers don't teach it. But that 2 is inside the grouping symbol, so it's definitely a horizontal change. And so that multiplication that's happening between the 2 and that set of parentheses is describing some kind of stretch or compression. And so what we have to do is we have to look for what that would be. So we're figuring out if that number is less than 1 or greater than 1. Now if the 2 had been outside of the trig function, if it was here in front, that would be a vertical stretch. But remember, horizontal changes feel backwards, so this is going to turn into a compression instead. And compressions bring a whole different level of difficulty in terms of graphing. So there's no vertical change, so we still go between 1 and -1. We still want our 4 tick marks going to 2 pi, but we know that we're going to shift to the right by pi over 2, so we also want to make sure to have that extra tick mark. I don't think I actually end up using it because of the compression, but it's better safe than sorry. I would rather have more tick marks than necessary than fewer. Alrighty, so there is our graph. So let's start with the parent sine function. Remember, it's that nice S shape. And now we're going to always do our compressions or stretches before translating, right? We have to deal with the multiplication before addition or subtraction. And so in order to compress this, what's going to happen is we need this S pattern to happen in half the time because of this 2. So I need to be able to fit 2 of these curves within our usual 2 pi. And so what we need to do is we need to cut these pieces into half so that we can make that distance half. Now if you're graphing this on paper for notes, I would use a different color of pen to put those inner tick marks. For the sake of making it clear where these points are, I'm going to label what they are. Alright? So from 0 to this black point was pi over 2. And so half of that we're now cutting pi into fourths. And so that's where I'm getting these values from, is they're fourths of pi's. Okay, so now to do our compression. So what I'm doing is I'm looking at the distance from each of our points to the y-axis because it's a horizontal change. And so I can count how many hops it is to get to that point, and I can divide that by 2. So this one is 2 hops away from the y-axis, so now it's only 1. This one goes to pi, so half of pi would be pi over 2. This one goes to 3 pi over 2, and half of that is 3 pi over 4. And this one goes to 2 pi, and so now it goes to 1 pi. And so if I were to copy this pattern, now I could fit 2 of them by the time I reach 2 pi. Now don't draw your lines yet, because we've only done one of our transformations. Now we need to do that phase shift. So what I'm going to do is figure out how many tick marks I need in order to take everything to the right by pi over 2. So do you see from 0 to pi over 2 is 2 hops now because I added extra tick marks? That means that I'm going to use 2 hops to move every single point here. And now, once you've done all those transformations, now draw in your curve. Now I can keep copying this pattern if I want to. Right? So here's like another iteration if I needed it. That's supposed to go through the origin. I just can't draw. Just kind of depending on what your needs are. So let's talk about some of these values, right? We didn't do any vertical changes, so it still goes from -1 to 1. Your midline's still at y equals 0 because there was no vertical shift. Your amplitude, it still goes from 0 to 1, so your amplitude is still 1. But our period is changing. Remember, to calculate the period, you do 2 pi and then divide it by the number of times this swoop happens between 0 and 2 pi. Or you could do 2 pi divided by b, which is 2, and you'll see that our period is pi. Alright, so here's another one. This one, now we're going to have 3 transformations in it. First, we need to get it written in the form that we can identify those transformations, right? So what that means is here within the cosine, I'm factoring a 3 out of this expression. So 3x divided by 3 is x, and 2 pi divided by 3 is -2 pi over 3. So we're going to need to identify what happens with the 3, what happens with the -2 pi over 3, and what happens with the 4. And those will determine what we need to do on our x and y axis. So the 3 is being multiplied inside the grouping symbol, so that's a horizontal change. When we're looking at vertical things, numbers bigger than 1 are usually stretches. And since this is horizontal, it'll be backwards. It'll be a compression. The -2 pi over 3 is a phase shift. It's a -2 pi over 3, so you feel like it should go to the left, so it's actually going to go to the right. And then that +4 is addition outside the grouping symbol, so that's a vertical change. And that the fact that it's addition is going to be a translation or a shift. I know how to spell translation. And it's going to go up because it's positive. So in terms of our axes, right, that translation of 4 up, normally we go between -1 and 1, but we need to add at least 4 new tick marks so that we can slide everything up by 4 points, right? Now here on the on the x-axis, we know we're going to go to the right by 2 pi over 3. So just be prepared to leave a little bit of space in case you need it on your graph. Don't go all the way here for your 2 pi, right? Okay, so I just left a little bit of space. Sometimes when we compress, though, we don't always need extra tick marks to the right, so I'm not adding them on until I know. Part of that's because I'm lazy, part of that's because I don't want to make the graph more complex than it needs to be. Okay, let's try it now. So this is a cosine function, so you need to make sure you have your little cosine U shape. Alright, and I'm just going to go deal with all the multiplication stuff before any of the addition stuff. So this 3 is saying that I'm going to take each of these points and cut their distance to the y-axis into 3. I'm going to have 1/3 the distance, because I need to be able to do this U shape 3 times before 2 pi. So the easiest way that I have found to do this is to go in here and add tick marks between my points. So see how from 0 to pi over 2 was 1 hop? Now it's 3 hops. I determine that based off of that horizontal change, or that b value. And so what that does is that makes it to where when I put these anchor points, at every tick mark is now when it moves. Like that. And so now I could fit 3 of these by 2 pi. Alright, so now that we've compressed it, now we're going to do our phase shift to the right. So remember, a phase shift is moving everything at the same time. And so I don't know what 2 pi over 3 is. Like, how many tick marks is that? Look at that. Remember, this is 2/3 of pi. So if I look at how many tick marks I have to make pi, I would use 2/3 of those to move to the right. So some of you guys learn easier when we have like fraction bars, so I'm going to try doing that. So do you see how it's 6 hops to make pi now because of our extra tick marks? So there's a bar cut in sixths. And if I want 2/3 of that bar, what that means is for every 3 of these, I'm going to go ahead and color in 2 of them. Alright, so here's a set of 3, so I'm going to color in 2 of them. And here's a set of 3, so I'm going to color in 2 of them. So how many boxes did I end up shading? Well, I shaded 4 boxes. So what that means in terms of our graph is for our phase shift, I'm going to scoot each of these over by 4 boxes. So, or by 4 tick marks. 2, 3, 4. 1, 2, 3, 4. Alright, so remember with the phase shift, you move them all the same distance. So there, I've moved it all to the right by 4 tick marks because that's what negative 2 pi over 3 is. And then I have a translation up by 4 tick marks. So if it's at 1, it'll go up to 5. If it's at 0, it'll go up to 4. And if it's at negative 1, it'll go up to 3. And so that is where our graph will end up at. And so now we need to go ahead and use our drawing tool to make our smooth curve. Alright, now I can copy more iterations of this, but because they're so far from the axis, it's kind of hard to tell where my points would be, so I don't necessarily want to do that. So let's describe some of these. So let's do minimum, maximum, and midline. So our minimum, right, is now at 3 because everything was moved up by 4. And our maximum is 5. Now halfway between my minimum and my maximum, I have my midline. So halfway between 3 and 5 is 4. That's because I had a vertical shift up by 4. Our phase shift was that movement to the right by 2 pi over 3. Now our amplitude, our distance from our midline to our maximum, is still 1. All right, we didn't vertically stretch or compress the graph at all. And then in terms of our period, I do 2 pi divided by b, so 2 pi divided by 3, and that's my period. Whew, I did a lot of examples with y'all. Alrighty, so now our next one is a tangent function. So that's a little bit of a change of pace, right? In terms of the x-axis, the tangent function usually goes between pi over 2 and negative pi over 2. So let's identify our transformations. So the 2 that's here is multiplied to the tangent, so that's a vertical stretch. The 1/4 that's there is being multiplied to the x, which there's nothing being added or subtracted in the grouping symbol, so x is kind of in there by itself. But you could see that's a horizontal change. And because 1/4 is less than 1, that'll be a horizontal compression. No, horizontal stretch, because it's backwards when it's horizontal. Sometimes I forget too. This is saying it'll take 4 times as long on the x-axis to make the tangent shape, so just be aware of that. And then the -3 is a slide down by 3, or vertical shift. I'm trying to decide how I want to say this. I'm going to say down 3. Okay, so let's think about how to tick mark our x-axis, because that's what really determines kind of where our anchor points go, right? So on a normal tangent function, it normally goes between negative pi over 2 and pi over 2. If we have our vertical stretch, that means our anchor points on the outside are going to go to 2 and negative 2. But we are also going to be scooting stuff down by 3, so we need to make sure to put lots more tick marks. I need to change that axis a lot. Right? Because I'm stretching it to go between 2 and negative 2, but then if I move it down by 3, I need at least a tick mark at negative 5. This is why we identify our transformations first, right? Because I would have messed up that graph. Okay. So we dealt with our axis in terms of the vertical stretch. In terms of the horizontal stretch, this 1/4 is saying that it takes 4 times as long to make this pattern, to make the little woo. Sounded like the DuckTales. Anyway, so if I take from 0 to pi over 2 and I multiply that by 4, I get 2 pi. So that's what I'm going to do, is I'm going to take this out to 2 pi. Alright, so for the sake of keeping things clean. Now remember, these things are kind of strange, the tangent function is, because half of it is on the positive axis and half of it's on the negative axis. So these tick marks on the negative axis are just as important as the positive ones. Alrighty. Now normally, I'm trying to decide how I want to do this. Normally we have vertical asymptotes here at negative pi over 2 and pi over 2. But because of the horizontal stretch, that's what's causing my horizontal asymptotes to happen at 2 pi and negative 2 pi. because instead of it going 1 tick mark to the right and 1 tick mark to the left, they go 4 now. All right, now halfway between our asymptotes, we would still have our 0. Okay, now I'm going to go ahead and put my parent function on here with the anchor points where it would normally go. And we're gonna do some of these anchor point changes. Okay, so our horizontal stretch, we know we'll move them out 4 times as much as they normally would go. Oops. Yeah. So this one is normally at pi over 4. If I do that 4 times as much, pi over 4 times 4 is pi. This one's at negative pi over 4, so it'll go to negative pi. So there's our horizontal stretch. Now see how they're equidistant between the middle and your new asymptotes? So there's our horizontal stretch. Our vertical stretch says that this distance, instead of being 1, should go up by 2 and down by 2. So there's our vertical stretch. And then that minus 3 is saying to take each of these points and take it down 3. So this one at negative 2 is at negative 5. Here we're at negative 3, and this one would be at negative 1. Alright, so we did our 3 transformations, and now we can draw in our shape. This tends to be very difficult for people to draw. This one will go kind of like that. And remember, these become almost parallel to that asymptote. Alright, so our period. How long did it take to do this? What I'm actually going to do to find my period is I'm going to take the usual period, which is pi, and divide it by b. So pi divided by 1/4. That is 4 pi. Because it took 4 pi to do one iteration of this. Some of it's in the negative area, but it's negative 2 pi here, right? So physical distance, there's 2 pi, and there's 2 pi. That's why the period is 4 pi. Now, an amplitude is describing the distance from the middle to the top of the graph, but tangent functions go for forever vertically, and so there is no amplitude on a tangent. In terms of a phase shift, we did not scoot these points to the left or to the right, right? Nothing was added or subtracted in the grouping symbol. So our phase shift here was 0. Our vertical shift was when we scooted the graph down by 3. These graphs continue forever downward, so there's no minimum. They continue upward forever, so there's no maximum. And we don't really describe a midline for the tangent function. That's usually just the sine or the cosine. Alright, so here's number 9. Now we're doing a cotangent. So remember, the cotangent is just flipped backwards from the tangent, right? It also changes the asymptotes. So if I'm identifying my transformations here, that plus pi over 6 is going to be a phase shift. Because it's addition, it's going to be going to the left by pi over 6. Alrighty, so what I tend to do with tangent functions, more so than with sine and cosine, is we need to identify where our asymptotes are. That's gonna be the real thing that we care about. Alright? So in this situation, remember the cotangent, well, the tangent is the sine divided by the cosine. So the cotangent of an angle is the cosine divided by the sine. And so we will have asymptotes wherever the sine is equal to 0. Alright, so if I look at my graph, my sine or my y values are 0 at 0 and pi radians. So there's 0, and then here's pi. Okay. Now I'm just going to use a couple of anchor points to talk about my asymptote. Oops. Come back. There we go. So normally we would have asymptotes here at these points, because that's where the sine is 0. But this is saying that we're going to be scooting everything to the left by pi over 6. So what we need to do is we need to cut these tick marks into sixths so that we will know what pi over 6 is, because right now pi is 1 tick mark. So there's in halves, there's in sixths. And so we're going to do that a few times. All right, so now each of those tick marks is cut into sixths. So our asymptotes are all going to be scooted to the left by pi over 6. Got to add an extra asymptote there. So scoot, 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 scoot. And so now where those anchor points that I put are, that's where we're going to draw in all of our vertical asymptotes. I'm going to do it in yellow. And since this is the only transformation that's happening, we can easily put our anchor points for the graph and graph it. Alright, so there's all of our asymptotes. Very terribly drawn because I don't know how to draw. So now what we need to do is now we need to go ahead and plot our zeros of our function. So I'm going to move my anchor points back so that I can use them again to talk about my zeros. So between each asymptote, halfway between, we're going to have a 0. And so do you see how there's 1, 2, 3, 4, 5, 6 hops between each asymptote? That means 3 hops from each asymptote is the halfway marker. And so that's what we're going to do on each of these. So those are our intercepts. Now we're also going to need anchor points where we go halfway between these, and then we go up by 1, because that's what they do, right? And so I'm just going to draw those anchor points in. So halfway between here and here, this here is currently divided into thirds, so it's between right there. So I'm just adding a couple of tick marks so that I know where to put those points. So again, halfway between these, and then halfway between these. The tangent function gets a little whack, right? It's kind of hard to draw. And so those are where we need to have our anchor points. So here at 1, and then down here at -1. And it'll be at all of those nice red tick marks. One was a little too high. There we go. -1. And while the tangent function is always increasing, the cotangent is always decreasing. That's why these are going kind of downhill. And then we're going to draw our curve. Well, we're going to kind of draw our curves. I really struggle with my aim because my tablet doesn't have a screen on it, so I'm trying to get my pen to match what my eyes are seeing. Alright, so let's look at this. There's no minimum, no maximum, no midline because it's a tangent function. We had a phase shift to the left by pi over 6. We did not have a vertical shift. There's no amplitude. And our period, we did not do any horizontal stretches or compression, right? So that means your period is pi. Alright, now we're going to do the cosecant, and then I will call it quits because this is a very long video. So for the cosecant, first what we're going to do is figure out, like, the cosecant is the opposite of the sine function. So I'm actually going to start by graphing a sine function and then use that to help me with my cosecant, alright? So I need this to be in the correct form with the double parentheses. So I can't have a negative here in front of the x like that. So I'm factoring a -1 out. Okay. So now we are going to have that negative. That one's going to be kind of a bear. It's going to cause us to have a horizontal reflection. That plus pi over 4 is a phase shift. Now not only is a phase shift, it's positive, so it's a left phase shift. And then that -2 is a vertical shift. It's going to go down by 2. Alrighty. So again, the cosecant is the opposite of the sine. So I need to prepare a sine function graph. So I'm going to go from -2 pi to pi, or to 2 pi, sorry. Okay. And so the sine parent function, oh, need to put tick marks, don't I? Now it normally goes between 1 and -1. But remember, we're shifting it down by 2 units. So make sure to go at least to -3. There we go. Alright, so we're going to do a couple of these things right away. So first I'm doing a horizontal reflection. So what we were doing is we were taking this graph and flipping it to face this other direction. So this one that goes out to pi over 2 is now going to go to -pi over 2. To positive pi will go to -pi. So we're just sending these to their counterparts. That's what that horizontal reflection does. Now what I need to do is I need to go to the left by pi over 4 units. But we don't have our bar broken into fourths, right? It's just broken into pi over 2s. So I need to go in and add tick marks so that I can scoot all of these over to the left by an additional pi over 4. And I don't have a long enough bar, so I'm going to add on to it. That'll be -9 pi over 4. Alright, so each of these is going to get scooted over to the left by 1 tick mark. Alright, so we did our horizontal reflection. We did our left phase shift. Now we need to do our downward shift by 2 for each of these. There we go. I'm just trying to make it look a little bit better. There we go. Alrighty. So now that we've done that, remember the cosecant graph has asymptotes on it. So what I need to do is back up before that downshift. Alright, so I'm going to scoot these back up too. Sorry, and the reason why will be apparent in just a second. Okay, so this is back to where it was before we scooted everything down. So before you scoot it down, what we need to do is we need to put in our asymptotes where these are 0. Alright, so that's what I'm doing real quick. So there's an asymptote here, here, and here. And then we can scoot it down because we know where those asymptotes were. Remember, our amplitude is our amplitude's 1. So that'll help you if you're getting funky shapes on your graph, right? Alright, so there is our graph. And so what the cosecant function does is it comes here to these points and it kind of makes like a weird like kind of cup shape like this. So that was a minimum, so it goes down. This one was a maximum, so it goes up. And then it would just keep repeating that pattern, down and up and down and up and down and up. Alright, so the period of this, so how long does it take from negative pi over 4 to negative 5 pi over 4? Alright, we didn't do any horizontal stretches or compressions, so that period matches the period of the sine function, which is 2 pi. These don't have amplitudes because they continue forever up and down. They don't have minimums or maximums because of that. I don't really know if these things have a midline. I mean, if it does, it's at negative 2, but the function doesn't ever get there. So I'm going to say there's no midline. I'll be honest, I'm not 100% sure on that. In terms of our phase shift, we went to the left by pi over 4. And in terms of our vertical shift, we went down by 2. Alrighty guys, I hope that this helped at least a little bit to see how to graph, and I hope at least some of you guys watch it. Until next time.